Okay, so good evening and welcome to today's live session for week 5 for the course Elements of Mechanical Vibration NOC25-ae17, and we are into the week 5 live session. We have already completed 4 live sessions up till now where we have gone through the basics of mechanical vibration. We have talked about single degree of freedom system, damped and undamped. How can we model a physical system as a single degree of freedom system in order to analyze what is going to be its natural frequency, etc. Then we have worked upon if my single degree of freedom system is subjected to harmonic excitation, and that will be extended in today's live session. And I hope that every one of you have already gone through the lectures for this week, and it is basically concerned about how the system is a single degree of freedom system is going to behave if we have the base excitation, which means that if my mass is attached to a base via a damper and a spring, and then that base is excited. Okay, it has a displacement excitation, then how my system is going to behave. And we'll work upon some questions so that it will be easier for you to solve the assignment problems. Okay, so coming on to question number 1. In question number 1, we have at what value of frequency ratio does the displacement transmissibility ratio becomes independent of the damping ratio for a single degree of freedom system with base excitation? So firstly, the question is about a single degree of freedom system, which is a mass, spring, damper, and then this is the base. Okay, so if this mass is having a displacement x, the base is having a displacement y. Okay, so this is a single degree of freedom system with base excitation. The base y, it can be written as y naught sine of omega t. Let this be k and c. Okay, I hope this is clear. So the question says that about displacement transmissibility ratio. Okay, and when does it become independent of the damping ratio? So firstly, damping ratio is what? Eta, which is nothing but c by cc, and we have cc as twice of under root mk. Okay, now also we have omega, which is the excitation frequency. We have omega n, which is the natural frequency of the system. Okay, and then we define the frequency ratio R as omega by omega n. Okay, so the displacement transmissibility, which is x by y. X is such that if we write the solution x as x sine of omega t minus phi, then this ratio of x, which is the amplitude of the response of my mass, and y, we should write it as y is the amplitude of the excitation. Okay, displacement excitation. So displacement transmissibility is defined as x by y, which is equals to 1 plus 2 eta r square divided by 1 minus r square whole square plus 2 eta r square to the power 1 by 2. This is the equation for displacement transmissibility ratio. Okay. So the question says that at what frequency ratio is this equation be changed in such a way such that we get that the displacement transmissibility does not change with the value of damping. Okay. So if you'll look at this question, this equation very closely, what are you going to get? In the numerator, we have 1 plus 2 eta r whole square. And then we have in the denominator, we have 2 eta r square. Okay. But there is this one term 1 minus r square whole square. This is making the difference. Okay. So if we have the value of this term such that it is equal to 1, such that it is equal to 1 or minus 1, we are going to get the same numerator and denominator. The values of eta are going to get cancelled and we are going to get x and y as a constant. Okay, we are going to get x and y as a constant, right? So if I assume that my 1 minus r square is equal to 1, 1 minus r square is equal to 1, what is going to happen? 1 will get cancelled and we are going to get r is equals to 0. R is equals to 0, but that is not what we want. We want r to have some value, right? Then only it will be equal to 1, isn't it? Because see, r cannot be 0. If we are having r as equal to 0, it means that sine of omega t, where omega is going to be 0. And if omega is 0, it is not a sinusoidal excitation, right? It is not going to be a sinusoidal excitation. But if I take 1 minus r square as minus 1, then r square is going to be 2 and r is going to be under root of 2, right? So for r is equals to under root 2, what are we going to get? For r is equals to under root 2, we have x by y is equals to under root of 1 plus 2 eta under root 2 square divided by 1 minus 2 whole square plus 2 eta under root 2 square. This will give us 1 plus 2. We can just write it as 8 eta square divided by 1 plus 8 eta square. This will get cancelled and we are going to get as 1. X by y is equals to 1. More than that, what is important over here is that whatever be the value of eta, we are always going to get the value of transmissibility ratio as 1. It becomes independent of the value of eta, which is the damping ratio. Independent of eta. Damping ratio value. Okay, it is independent of the value of eta. Now, if this is the case, then at r is equals to under root 2 or when omega is equals to under root 2 of omega n, the system is going to have the mass m is going to oscillate with an amplitude x, which will be equal to the amplitude of the displacement, which will be equal to the amplitude of the displacement of the base. Correct? And it becomes independent of eta. For this, I have also taken the graph from the book S.S. Rao. So as you can see over here, there are different plots of the transmissibility ratio with the frequency ratio R. And it may be observed over here that as frequency ratio changes, we get a peak at around the frequency ratio R is equals to 1, which is true also because we are going to get the maximum peak at resonance. However, after omega by omega n is equals to under root 2, we see that the displacement transmissibility ratio becomes less than 1. It becomes less than 1 for all values of eta, right? For all values of eta. Along with that, you can observe over here that at this point, at this point, what is happening? X by y is equals to 1 for all values of eta, right? For all values of eta. And this is happening at what? At this. R is equals to under root 2. So you can see from the graph as well that this is true. For the frequency ratio under root 2, we are going to have a constant value of displacement transmissibility, and it is independent of the value of eta, right? So for the given question, which asks that at what value of frequency ratio does the displacement transmissibility ratio becomes independent of the damping ratio for a single degree of freedom system with base excitation, the answer is omega by omega n r is equals to under root 2, and this is the. Now coming on to question number 2. This again is a question about base excitation, where base is having some kind of a displacement excitation. So it says that a vehicle can be modeled as a single degree of freedom system with mass 1200 kg, stiffness 400 kilonewton, and damping ratio is 0.5. If the vehicle is traveling on a road with sinusoidal profile having amplitude of 0.05 meter and wavelength of 6 meter with a speed of 20 km per hour, find the amplitude of vertical vibration of the vehicle. Okay. So we have a vehicle such that this is the mass of the vehicle. It has a stiffness of 400 kilonewton per meter. There is a damper such that the damping ratio eta is equals to 0.5. Okay. And since it's a vehicle, it is going to have some tires. Let us say these are the tires. And it is traveling on a road. The road is such that it is having a sinusoidal profile. Okay. And it has a wavelength of, just write it. It has a wavelength lambda is equals to 6 meter. Okay. Now the forward speed of this vehicle is 20 kilometer per hour. And we have to find the amplitude of vertical vibration, which is this one. If let us say that this is something like x cos of omega t minus phi, then we have to find the value of this x. Okay, we have to find the value of this. Now in the question, we have the mass, stiffness, damping ratio, forward speed, just 20 kilometer per hour. Then we have wavelength lambda. Okay, it is already written wavelength. Yeah. So these are the specifications that we have. So the first thing is, even if I want to like apply the equation that we have for the displacement transmissibility, it is like x by y is equals to 1 plus 2 eta r whole square divided by 1 minus r square whole square plus 2 eta r whole square to the power 1 by 2. So I have the value of eta, but I need to find out the value of r, okay, which is omega by omega n. So I don't have directly the values of omega and omega n, but I have the necessary data in order to find out the values of omega and omega n. So first we'll calculate omega n. So for a single degree of freedom system, we have the natural frequency defined as under root k by m, which is 400. It was 400 kilonewton. So 400 into 10 to the power 3 divided by mass, which was 1200. Okay, so if you are going to calculate this, it is going to give you the value of omega n as 18.257 radians per second. This is the value of omega n, which is the natural frequency, right? Now, if I see the value of omega, I if I would have had the value of frequency f, I can find the value of omega by the equation 2 pi f. Okay, but how do I find the value of frequency f? Sorry. So, in order to find the frequency, if I have the wavelength and I have the speed, if you remember that when we study about the waves, we have this equation that f is equals to v by lambda, where v is the wave speed and lambda is the wavelength, right? So if I have these two values, I can find the value of f. Now over here, we don't have the wave speed, but instead we are going to use the vehicle speed. Okay, because the vehicle is traveling on that road which is having a wavelength of lambda. So that speed of the vehicle is going to be used in order to find the value of frequency f. Okay, again, this v is given in kilometer per hour, so we can write v as, it was 20 kilometer per hour as I remember. Yes, so this can be written as 20 changing kilometer into meter, and then per hour is 60 into 60, 60 minutes 60 seconds. So if I put this over here, 2 pi into 20 divided by 3600 into 1 by 6. After doing all the calculations, this will turn out to be 5.81778 radians per second. Okay, so we are going to get R as omega by omega n, which will be 5.81778 divided by 18.257. And when you will calculate this, it will turn out to be 0.318653. Okay, so when I put these values in the displacement transmissibility equation, I get x by y. Okay, I'll again write the equation over here. 2 eta r square divided by 1 minus r square whole square plus 2 eta r to the power 1 by 2. It will turn out to be 1 plus 2 eta r, which is 0.318653 square, divided by 1 minus 0.318653 square whole square plus 2 eta 0.318653 square is whole to the power 1 by 2. Now, after doing all the calculation, you can get the final value. However, I will not go through the calculating part. I've already done the calculation. X by y will come out as 1.1000964. This is the value of the transmissibility ratio. However, in the question, it is asking find the amplitude of vertical vibration. Okay, if you look over here, we have the amplitude of the sinusoidal profile as 0.05 meters, right? So we have this value as 0.05 meter, which is nothing but y. Now, since I have the ratio of x by y, I can simply write the value of x as 1.1000964 into 0.05, which will give 0.055048 meters. So this is the amplitude of vertical vibration of the vehicle. Okay. So I hope this is clear. Coming on to question number 3. Okay. Now the question number 3 says that a heavy machine weighing 3000 Newton is supported on a resilient foundation. The static deflection of the foundation due to the weight of the machine is found to be 7.5 centimeter. So if I write the weight of the machine, 3000 Newton. Then we have delta static as 7.5 centimeter. Delta static is nothing but the static deflection of the foundation. It is observed that the machine vibrates with an amplitude of 1 centimeter when the base of the foundation is subjected to harmonic oscillation at the undamped natural frequency of the system with an amplitude of this. Find. Okay, so first we'll write these things. Firstly, omega is equals to omega n. Okay, so let us say that this is a machine m. Then it is supported something like this to the base. This is C, this is Q. The base is oscillating something like this with y sine of omega n t, because omega is equals to omega n. And then we have the value of y as 0.25 centimeter. And the machine is oscillating as x, which may be written as x sine of omega n t minus phi, where x is 1 centimeter. Okay. So firstly, we have taken the response of x as capital X sine of omega nt minus phi, because the mass is going to oscillate at a frequency of at which the base is exciting, right? Now the base is exciting at omega n. We have a damper, because of which the transient, which is because of the natural frequency of the system, it is going to die out with time, and we are concentrating only on the steady state vibration of the system. So this is the case. Okay. So now I have all these values. I'm supposed to find first the damping constant of the foundation. So the first thing that comes in my mind is that I have X, capital X value, I have capital Y value, and I know the transmissibility ratio equation. So I can just put these values over there and I can find out the relation between eta and R. Now, since I already know the value of R, it should be taken as 1 because the system is oscillating at the natural frequency. So R is going to be 1. So using the transmissibility ratio equation, I can find out the value of eta, correct? Firstly, writing again the transmissibility ratio equation. Yeah. So we have x by y 1 plus 2 eta r square divided by under root of, okay, under root we can keep 1 minus r square whole square plus 2 eta r whole square to the power 1 by 2. Now since r is equals to 1, we have x by y as 1 plus 4 eta square divided by 4 eta square to the power 1 by 2. Now if I put the values of capital X and capital Y, I get this as equal to 4. Squaring on both sides give squaring on both sides give 1 plus 4 eta square divided by 4 eta square is equals to 4 into 4, 16. This implies 1 plus 4 eta square is equals to 64 eta square, or 60 eta square is equals to 1. This implies eta is equals to under root of 1 by 60. This value will turn out to be 0.1291. This gives the value of the damping ratio. This gives the value of damping ratio. But in the question, we are supposed to find out the damping constant. Now we know that C is equals to eta into Cc, and Cc is nothing but twice of under root m into k, right? So we have twice of under root m. We have a mass value of 3000 divided by 9.81, And then we have the stiffness K as, okay, so we don't have the stiffness value, but we have the static deflection. Now, if you remember, the static deflection happens because of the presence of the spring. Okay, so the static deflection delta ST is nothing but mg by k. So we have mg as 3000, k as 3000 divided by delta ST, which is nothing but 7.5 centimeters. 7.5, and we'll convert it into meters, so we are going to have 100 over here. Now, if you'll do all the calculation, you are going to get the value of K as 40,000 Newton per meter. So you can put it over here and get 40,000, right? Now, C is equals to eta 0.1291 into 2 into under root of 3000 into 40,000 divided by 9.81. So if you'll do all the calculation, this value will turn out to be 903.0512 Newton second per meter. And this is the answer to the part A. Okay, this gives the damping constant. Second thing is we have to find out the dynamic force amplitude on the base. Okay, dynamic force on the base. So if you have seen the equation or read the book or you have gone through the lectures, there is this equation for finding out the force, and when you solve it somewhat, you are going to get the relation of finding the force as Ft by K into Y will turn out to be R square into 1 plus 2 eta R whole square divided by 1 minus R square whole square plus 2 eta R whole square. Okay, since in our case R is equal to 1, R is equal to 1, so Ft is going to be K pi into 1 plus 4 eta square divided by 4 eta square to the power 1 by 2. Okay. Now, there is one thing very interesting over here. As we know that there is a relation such that x by y is equals to 1 plus 2 eta r whole square divided by 1 minus r square whole square plus 2 eta r whole square to the power 1 by 2. Now, since r is equals to 1, this turns out to be x is equals to y into 1 plus 4 eta square divided by 4 eta square to the power 1 by 2. Right. So we can replace y into this thing as x, and this will turn out to be k into x. We already have the value of x and k, right? So k value we calculated over here, and for the value of x we already have it with an amplitude of 1 centimeter. So if we put these values over here, we get f of t as 40,000 into 1 by 100. This will turn out to be 400 Newton. This is the answer to the part B. So 400 Newton is the force that is being applied on the base. It is the force that is being applied on the base. Okay. Now the part C, which says that or asks that the amplitude of the displacement of the machine relative to the base. Okay. So when we are saying relative to the base, we are talking about Z, which is nothing but X, not capital X actually, X minus Y. So if we write an equation in terms of Z, which is the difference between X and Y, so this is basically the relative value between X with respect to Y. Now if we use this and then we find the equation of motion and then we use it to get a solution, we are again going to get a relation, in the form of an equation such that Z is equals to capital Z, again amplitude. Here it should be small z. So capital Z is equals to y into r square divided by under root of 1 minus r square whole square plus 2 eta r whole square plus 2 eta r whole square, right? Since r is equals to 1, r is equals to 1. What do we get? We get z is equals to y divided by twice of eta. The value of y we already have in the question, which is given as 0.25 centimeters. So 0.25 divided by 2 into 0.1291 into 100. This will give the value 0.00968 meter. And this is the answer to the part C. Okay, I hope this is clear. So coming on to question number 4. In question number 4, we have an electric. So up till now, we solved questions which were related to base excitation, where we had a single degree of freedom system which was attached to a base, and the base was itself having a displacement excitation of the form y sine of omega t. Now this question is about eccentric mass. When there is the presence of, for a rotor, there is some eccentric mass, it causes some kind of a excitation. Okay, it is also a sinusoidal excitation in the system. However, the relations are somewhat different as compared to a harmonically excited system. So the question says that there's an electric motor of mass m mounted on an elastic foundation. It is found to vibrate with a deflection of 0.15 meter at resonance. It is known that the unbalanced mass of the motor is 8% of the mass of the rotor due to the manufacturing tolerances used, and the damping ratio of the foundation is 0.025. Determine the eccentricity of the radial location of the unbalanced mass E. Okay, so first things first, we'll first solve the part A of the question. See, our system is something like we have the motor mass as m. It is mounted on an elastic foundation, and then deflection is 0.15 meter at resonance. Okay, deflection of what? Deflection of definitely the motor mass, right? It is found out to be 0.15. So we have x as 0.15 meter. It is known that the unbalanced mass of the rotor of the motor is 8% of the mass of the rotor. M is 8% of rotor, which is equals to 0.08 of M, right? The damping ratio of the foundation is 0.025. First, we have to find the eccentricity of the radial location of the unbalanced mass. So see, if you remember, for eccentric mass, transmissibility ratio was given in the form such that mx by me was equal to r square divided by 1 minus r square whole square plus 2 eta r whole square under root. Okay. Now in the question, we have the deflection as 0.15 meter at the resonance, which means r, so omega by omega n, is equal to 1. So we have mx by me as 1 by 2 eta. 1 by 2 eta. Correct? So for this, I have the value of eta. I have the value of capital M. I have the value of small m. I want to find out the value of E, and I have the value of capital X. So I'll use that. I can write this equation in the form E is equals to mx 2 eta divided by small m. If I put these values, E is equal to 2 into m into 0.025 divided by 0.08 of capital M. So this will get cancelled. And finally, this is going to give us a value of eccentricity as 0.09375 meter. Okay, we get the value of eccentricity as this. Now B, I have to find the peak deflection of motor when the frequency ratio varies from resonance. See, it means that we have to find the peak deflection other than the resonance. Okay, so if I want to find the peak deflection, firstly I need to know that what is going to be the peak deflection and at what value of let us say deflection are we going to get a peak deflection, right? So firstly, the deflection is given by the form mx by me is equals to r square divided by 1 minus r square plus 2 eta r whole square. Now, in order to find the peak deflection, we need to know that what is going to be the peak deflection. For that, what do? We differentiate it, right? We differentiate it with respect to r, and then by using that value of r, we are going to get the equation for the peak deflection. So if when I differentiate this, if I differentiate d of mx by me with respect to dr, and then I put it equal to 0. Then I get that this happens at r is equals to 1 by under root of 1 minus 2 eta square at peak deflection is obtained. Okay, so if I put the value of r in the equation mx by me, what do we get? We get mx by me max as 1 by 1 minus 2 eta square divided by under root of 1 minus 1 by under root of, okay, under root, since we have a square, it will become 1 minus 2 eta square whole square plus 2 eta divided by under root of 1 minus 2 eta square whole square, right? This will give us the value 1 by 1 minus 2 eta square divided by, if you look at this, what do we get? 1 minus 2 eta square minus 1 divided by 1 minus 2 eta square. 1 will get cancelled, and so we are going to get 4 eta to the power 4 divided by 1 minus 2 eta square square plus we'll have 4 eta square divided by 1 minus 2 eta square, right? Now if I take the, there should be a under root as well. Okay. Now if I take the denominator common for the denominator, what do I get? 1 by 1 minus 2 eta square divided by under root of 4 eta to the power 4 plus 4 eta square 1 minus 2 eta square, and then we'll have a 1 minus eta square in the division, which will come above as multiplication, and this will get cancelled. Alright, so in the denominator, what are we getting? We have a 4 eta square, and we have a minus of 4 eta to the power 4. We have a mx by me max as 1 by under root of 4 eta square minus 4 eta to the power 4. This will give us 1 by 2 eta into under root of 1 minus eta square. This is going to be the maximum or peak deflection. Now I can simply put the value of eta over here and get the peak deflection, right? It's very easy. So mx by me is equal to 1 by 2 into 0.025 into under root of 1 minus 0.025 whole square will give 20.0063. So X max will be 20.0063 into 0.08 capital M into eccentricity, which was 0.09375, 0.09375 divided by capital M. After doing the calculation, X max will turn out to be 0.150047 meters. So this is the peak deflection. Okay. Coming on to the third part of the question, which says that the additional mass to be added uniformly to the motor if the deflection of the motor at resonance is to be reduced to 0.1 meter. Now, currently the deflection at resonance of the motor is what? It is 0.15 meter. But now the question says that if I want it to be 0.1 meter, what should I do? So, adding another slide. So we have the equation of the form mx by me is 1 by 2 eta for r is equals to 1. That is the resonance. Okay. Now we have to replace m by m plus ma, which is the additional mass. This is the additional mass. So the question is asking that what should be this additional mass such that capital X, it changes from 0.15 meters to 0.1 meter. So we are going to put all these values and find the value of m plus ma. So we'll have the new equation as m plus ma into 0.1 by 0.08 m into E is going to be 1 by 2 into 0.025, which is going to be 20. Yeah, the value of eta was 0.025. Okay, so m plus ma will be equal to 0.08 into 0.09375 divided by 2 into 0.05 into 0.1 m. After doing all the calculation, it is like m plus ma is going to be is going to be 1.5 m, and so ma is going to be 0.5 of m. So almost 50% extra of capital M, which is the mass of the rotor, should be added to the rotor again so as to get a deflection amplitude of 0.15. Okay. Now coming on to question number 5. which says that for a spring mass system, the mass is of 10 kg and the spring of stiffness 4000 Newton per meter. Vibrates on a horizontal surface. Okay. A coefficient of friction is 0.12. So when subjected to a harmonic force of amplitude 98 Newton and a frequency 2 Hertz, the mass is found to vibrate with an amplitude this. We have to find out what is the amplitude. Then we have to find out the limit of amplitude of the force to get a real value of amplitude of vibration. So firstly, the question is something like, you have a mass m and then there's a spring which has a stiffness of 4000 Newton meter. Okay. And it is having a forcing of 98 sine of 2 hertz. See, F is 2 hertz. So omega is what? 2 pi F, which is 2 pi into 2, 4 pi. 4 pi T. Okay. And here there is some friction such that mu is equals to 0.12. So we have to find out that this mass, if it is oscillating, definitely it is oscillating. So what is the amplitude of the oscillation of the mass? Okay. So see, firstly, for this kind of a system, what relation do we have? See, up till now we were dealing with a system wherein forcing was there and then we had a viscous damping. Here we have a coulomb damping. Okay. So there has been the derivation, whole derivation of what is the relation between the, or what is the transmissibility ratio for the coulomb damping, and it turns out to be x by y as, or actually x was given in terms of f naught by k into 1 minus 4 mu n by pi f naught whole square divided by 1 minus r square whole to the power 1 by 2. Mu is what? Coefficient of friction. Capital N is what? It is the normal force. Capital L is the, capital N is the normal force. F naught is the forcing. So if F can be written as F naught is nothing but 98 Newton. R is again omega by omega N. So we need to find out, we have omega, we need to find out omega N. And other than that, yeah, these are the values. And if you put these values, we are going to get the value of capital X. Firstly, we'll find the value of omega N. So for a single degree of freedom system, omega N is nothing but under root K by M, which is under root of 4000 by 10. So we have 20 radians per second. Then we have R as 4 pi by 20, which is pi by 5, and this will come out to be 0.6283. Okay. Now, if I put all these values, I get capital X as 98 by 4000 into 1 minus 4 into 0.12 into capital N. So capital N is the normal force. We know the mass, right? The mass is 10 kgs. So N is going to be what? 10 into 9.81. So it is going to be 98.1. 98.1 divided by pi into 98 to the power 2 divided by 1 minus 0.6283 whole square to the power 1 by 2. Okay. After doing all the calculation, which you can repeat, I have done all the calculation. X will turn out to be nearly equal to 0.04 meters. Okay, so this is going to be the amplitude of the vibration. Amplitude of vibration of the mass, considering the Coulomb damping. Second part of the question asks us, find the limit of the amplitude of the force to get a real value of amplitude of vibration. So this thing comes out from the concept that, see, over here we have capital X as F naught by K into 1 minus 4 mu n by pi F naught whole square divided by 1 minus r square whole square to the power 1 by 2. So if you look over here, the denominator is always going to be positive, right? But the numerator, it can be negative. And this whole is having a power of 1 by 2. So if 4 mu n by pi f naught square, if it is greater than 1, what is going to happen? We are going to have a negative value to the power 1 by 2, which will give us our imaginary value, which is not possible in physical world, right? The amplitude of vibration cannot be a imaginary value. Okay, so using that numerator, we can actually find out the limit of F naught. Okay, since we know we have a fixed value of friction, we have a fixed value of the normal force. Okay, but for the value of F naught, we need to find the limit. Okay, so if I use this equation, if I use the equation 1 minus 4 mu n by pi f naught square, it should be always greater than 0. What do I get? I get 4 mu n by pi f naught square. It should always be less than 1. It should always be, yeah, it should always be less than 1. Now this is going to happen when, if I take the square out, what is going to happen? I have 4 mu n by pi f naught. 4 mu n by pi f naught as what? As greater than 1. Right? I have this as greater than 1. Just a second. No, it should be less than only. It should be less than 1. If this whole value is going to be less than 1, then definitely only then its square is going to have a value less than 1. If it is greater than 1, it is never going to be greater than 1. So it should be less than 1. Now, if I take it like 4 mu n by pi should be less than f naught. Okay, so this will give us a relation f naught should be greater than 4 mu n by pi. If I put the values 4, 0.12 into 98.1 divided by pi, I get the value of f naught. It should be greater than 14.988 Newton. So f naught should be greater than 14.988 Newton for the equation to give us a real value of amplitude of oscillation of the mass m. Okay, so this gives us a limit of what should be the amplitude of the forcing that is being applied on the mass. Okay, I hope this is clear. So now we'll come on to question number 6. So question number 6 says that when an exhaust fan of mass 380 kg is supported on a spring with negligible damping, the resulting static deflection is found to be 45 mm. If the fan has a rotating unbalance of 0.15 kg meter, find A, the amplitude of vibration at 1750 rpm and the force transmitted to the ground at this speed. So this is again a question which is related to the rotating unbalance. So we have the exhaust fan mass as 380 kg, right? Then we have static deflection as 45 mm. We have eta is equals to 0 since it is saying that we have negligible damping. We have a rotating unbalance of 0.15 kg meter. See, it is written as kg meter, which means that m into E is given as 0.15 kg meter. Okay, now on the basis of these values, we need to find out what is asked in the question. So first is you have to find out the amplitude of vibration, right? Which can be found out using the equation, right? The equation that we have. See, we have x m by m e as what? R square divided by under root of 1 minus r square whole square plus 2 eta r whole square. Since eta is already equal to 0, we have x m by me as r square divided by under root of 1 minus r square whole square. Over here, you can have a question that why am I even bothering to write under root and then square? We know that under root of a square is going to be what? A. But for the time being, if I am using this, I'm assuming that a is greater than 0. Okay, but this equation is true for all the a's, whether it is positive or negative. If I directly write under root of a square as a, it will be true only for the positive values of a, right? Or what I can do is I need to write it as mod of a. That will be a correct mathematical form. Because no matter whether a is positive or negative, under root of a square is always going to be positive. So we can use a mod over here also. Okay, but for now, I am just leaving it like this. So we need to find out R, which is omega by omega n. Omega we already have because we have 1750 rpm, which we need to convert. So omega is nothing but 2 pi into 1750 divided by 60 because we have rotations per minute. So we'll convert it into per second by dividing it with 60. This will come out to be 183.26 radian per second, right? Now, in order to find omega n, we want the value of k and m. Value of m we already have. For the value of k, we have the static deflection, which is given as 45 mm. So we have delta static into k as m into g. This implies K is equal to 380 into 9.81 divided by delta static, which is 45 into 1000. Okay. This will give us a value of 82,840 Newton per meter. Okay. So using these values, actually, you can maybe use the ratio of delta ST and G as to find the value of natural frequency. Since we have something like this, K into delta static is equals to mg. So K by m is equals to G by delta static. So omega n, which is equals to under root of K by m, it is going to be equal to nothing but under root of G by delta static. Okay, so this will turn out to be 9.81 into 1000 divided by 45. This will also be equal to 82,840 divided by 380 and will give a value of 14.7648 radians per second. Okay, so now we can find the ratio as omega by omega n, which will be 183.26 divided by 14.7648, 12.412. Right? So now we can use this to find the value of capital X as, so we had mx by me as 12.412 square divided by under root of 1 minus 12.412 square. Apart from that, we also have the value of capital M and the multiplication of M and E. X will turn out to be 0.15 divided by 380 into 154.0566 divided by under root of, or not under root, we can simply write it as 153.0566. This will give us the value of X as 3.9732 into 10 to the power minus 4 meter, or 3 point, it should be 0.39732 mm. Okay, I hope this is clear. Coming on to second part of the question, which is talking about, we need to find out the force transmitted to the ground at this speed. Okay, so if you remember what we did earlier about force transmitted, which question was it? Here, yeah, dynamic force amplitude on the base. Okay, and we had the relation come out as kx. Similar to this, or the rotating unbalance as well, the force transmitted is going to be what? K into x, right? See, actually the force transmitted should be K into x plus C into x dot, right? But if you look about C into x dot, we have the damping as 0. So the force only will get transmitted because of the presence of the spring, okay? Because of its stiffness. In that case, we can simply write force transmitted as what? K into X, which is nothing but 82,840 into 3.9732 into 10 to the power minus 4. This will give us a value of 39.9140 Newton. This is the force transmitted, and this is essentially the answer to the part B of the question. This was the answer to the part A of the question. Okay, so for this question, we had only two things to find. We had to find out the amplitude of vibration and the force transmitted. Now we'll be coming on to the question number 7. See, in question number 7, we need to find out the equation of motion and the steady state angular amplitude of the bar. This kind of question we already did, right? We did it when we were having the, I think, week 2 or week 3 live session, when we had to find out the equation of motion of system of these kind, and we used either energy balance or we used by equating the forces and the moments that we'll get the equation of motion, right? In this case, we have a similar kind of a question. The only difference is that this point P of this point P of the spring is what? It is having a displacement vibration, which is given in the form x naught sine of omega t. This is the only difference. In the other question that we have solved till now, this point P was actually fixed. This time it is moving with x naught sine of omega t. What is important over here is to note that for a spring, if one end is having a movement and then other end is also not fixed but having a movement, then in that case the force that is being applied by the spring, it will depend on the relative displacement between the 2 points. Correct? It will depend on the relative displacement between the 2 points. Okay. So for this spring, I have this point and the spring and this. Okay. So now if I want to know that what is the force that is being applied by the spring, let us say for this we have already been given x of t as x naught sine of omega t. And for this, let us say that this part is going downward. We have, or let us say just for now that this is also in this direction. Let us say this is y. Okay. So the force by the spring is going to be nothing but k into y minus x. K into y minus x, which is what? Which is the relative deformation of the spring. Relative deformation of the spring. Okay. So now, if I consider this bar, this is the bar. Okay. and this was the original position of the bar. Let us say that it has this is the deflection theta. Okay, so in this case we are going to have a force, sorry, a force like this. Over here we are going to have a force like this. The dashpot we are going to have a force like this, and then we have the distances as L by 4, L by 4, and this distance is L by 4 plus L by 2, which will become 3L by 4. Okay, so what is going to be this force? This force is going to be K into Y minus X. Now what is this Y going to be? This Y, if I consider if theta is small, Y is going to be what? 3L by 4 into theta. Okay, we have L is equals to R theta for a small arc. So using that formula, we are going to get Y is equals to 3L by 4 into theta. Similarly, if I consider this as Z, we have Z as L by 4 into theta, and this is also going to be Z only, right? So this is going to be K 3L by 4 theta minus X of t. This is going to be C 3L by 4 theta dot. Okay, not 3L by 4, it should be L by 4. And this is going to be K L by 4 into theta. Right, and let us assume that for this rod, we have the I as the moment of inertia about O. Okay, so if I would write I theta double dot is equals to summation of all the moments about O, what am I going to write? I'm going to write I theta double dot is going to be C. Over here, we have the motion in this direction. The rotation is in this direction, right? Corresponding to this rotation, the inertia is going to be in this direction. But if I look about what the forces are acting, we have the moments in the counterclockwise direction. So the moments are going to have a negative value, right? So we'll have minus, firstly considering this one, which is K L by 4 into theta, K L by 4 theta into L by 4. Then we have minus C L by 4 theta dot into L by 4, C L by 4 theta dot into L by 4 minus K L by 4 theta K L by 4 3K L by 4 theta minus X of t into 3L by 4, right? It should be 3L by 4 And yeah, these three are going to contribute as the moments. For now, we are considering no mass. Okay. So what is this going to give us? I theta double dot is equals to minus k L square theta by 16 minus c L square theta dot by 16 minus 9k L square by 16 into theta and plus 3L by 4 into x of t. These both, the first and third terms, can be combined to give us 10 by 16, which is going to be 5 by 8. So minus 5 k L square by theta into theta by 8 minus c L square theta dot by 16 plus 3L by 4 x naught sine of omega t. This will give us I theta double dot plus 5 k L square by 8 into theta plus c L square by 16 into theta dot is equals to 3L by 4 x naught sine of omega t. Okay, there should be a k over here also, right? K. Yes. So this is going to be our equation of motion. Now, if you compare this with what we found out for a single degree of freedom system with forced excitation, this is somewhat similar to that, right? We had something of the form mx double dot plus kx plus cx dot is equals to f sine of omega t. So if we use this analogy and as asked in the question, the steady state angular amplitude, we can use the formula for a single degree of freedom system where we had x is equals to f naught by k minus m omega square whole square plus c square omega square to the power 1 by 2, we can get the expression for the steady state amplitude. Right? We know the value of k, m, omega. We just need to relate this, like we can relate like m is equals to I, not exactly equal to, but we can just relate m with I, and then we can relate k with 5k L square by 8, c with c L square by 16, and f with 3 KL x naught by 4. We can just put these things in this equation and we can get the relation of x, which is the steady state amplitude. Coming on to question number 8. So question number 8 says that an automobile weighing 1000 Newton empty and 3000 Newton fully loaded 3000 Newton fully loaded vibrates in vertical direction while traveling at 55 miles per hour on a rough road having a sinusoidal waveform with an amplitude y meter and a wavelength 12 meter. With an amplitude y meter and a wavelength 12 meter. Okay. Assuming that the automobile can be modeled as a single degree of freedom system with stiffness 30,000 Newton per meter and damping ratio 0.2, determine the amplitude of vibration of the automobile when it is empty and when it is fully loaded. Okay, so what do we have? We have an automobile which is having a stiffness and damping, and it is attached to a base which is having wheels, and it is going through a road which is having a sinusoidal waveform, waveform, something like this. Stiffness, damping, and mass. So we have K as 30,000 Newton per meter, and we have eta as 0.2. Plus we have mass as 1000 for empty and 3000 for fully loaded. Right. Now for this road we have this as y, it's given in terms of y, and we have a wavelength lambda is equals to 12 meters. Apart from that, we have the vehicle speed in the forward direction as 55 miles per hour. Okay. Now, we need to find out the amplitude of vibration of the automobile. So if this is of the form x, sine of omega t minus phi, we need to find out the value of x for both the cases, empty as well as fully loaded. Okay. So first we will do the, okay, first we should find out actually R, right? Because again we have the same relation which has x by y is equals to 1 plus 2 eta r whole square divided by 1 minus r square whole square plus 2 eta r whole square to the power 1 by 2, right? For eta we have the value, but we need to find the value of r. Now in this case, firstly we need to find the value of omega, which is going to be the same for both the cases, but the value of omega n is going to change for empty and fully loaded vehicle. So in order to find out omega, we have, if you remember, we had omega as 2 pi f, and f was nothing but v by lambda, where v was the speed and lambda was the wavelength. So v is given as 55 miles per hour. So we need to change it to meter per second in order to get the value of omega in radian per second. So omega is going to be 2 pi into 55 miles. If we convert it into kilometers, we need to multiply it with 1.60934 into 1000 divided by 3600 into 1 by 12, because 12 is the wavelength. This will give a value of omega as 12.8738 radians per second. Now for the case A, which is empty. Empty automobile. We have omega n as under root of k by m. The value of k is, just a second, 30,000. 30,000 divided by 1000 into 9.81. This is going to give a value of 17.1552. From this, we get the value of R as 12.8738 divided by 17.1552 as 0.7504. Now, if I use this equation in this displacement transmissibility equation, what are we going to get? We are going to get x is equals to y into 1 plus 2, sorry, 2 eta, which is 0.2, into r, which is 0.7504, whole square divided by 1 minus 0.7504 square whole square plus 2, 0.2 into 0.7504 whole square. This to the power 1 by 2. This will turn out to be y into under root of 1 plus 0.3002 square divided by 0.4369 square plus 0.3002 square. X will turn out to be 1.9696y. This is the answer for case A, which is for an empty automobile. Now for a fully loaded automobile, omega n is going to be under root of k by 3000 into 9.81. This value is going to be 9.9045 radians per second. Okay, so if you find the value of r, it will come out to be 12.8738 divided by 9.9045, which is 1.2998. And putting this in the equation of displacement transmissibility, x can be written as y into 1 plus 2 into 0.2 into 1.2998 whole square divided by 1 minus 0.2998 whole square plus 2 into 0.2 into 1.2998 square to the power 1 by 2. This will turn out to be y into 1 plus 0.51992 square divided by minus 0.6895 square plus 0.51992 square by 2. So x will turn out to be 1.7035 times of y. So if you look over here, the amplitude of oscillation for a fully loaded automobile is actually less as compared to a empty automobile, right? The excitation and everything is going to be the same, the road is going to be the same, but the amplitude is going to be reduced for a fully loaded automobile. So now we'll come to question number 9. The base of a damped spring mass system with mass 25 kg, K 2500 Newton per meter is subjected to a harmonic excitation of y naught sine of omega t. The amplitude of the mass is found to be 0.05 meter when the base is excited at the natural frequency of the system with y naught is equals to 0.01 meter. Determine the damping constant of the system. See, again we have a base excited system. We have mass which is attached with a spring and a dashpot to a base such that the base is having an excitation y and the mass is having an excitation of small x. Not excitation, actually it is vibrating at a response x. We have mass is equals to 25 kg, K as 2500 Newton per meter, and Y as Y naught sine of omega t, where the value of Y naught is already given as 0.01 meters. Apart from that, we also know that if M is having a motion x as x naught sine of omega t minus phi, the value of x naught is 0.05 meters. Okay, we need to determine the damping constant of the system. The first thing that is to be kept in mind in this question is that the natural frequency of the system is actually used for the excitation. So we have omega as omega n. So the form of the displacement transmissibility, which is in terms of eta and omega n, it should not be used over here, right? The reason being that if we use it, okay, what are we going to get? What are we going to get? If you remember that for the first question that we did, we had that if the ratio of frequency, if it was equal to 0 or if it was equal to under root of 2, okay, we had the displacement's transmissibility as 1, and in that case, this was not depending upon eta, right? Over here, we don't have under root 2 or 0. We actually have omega by omega n as what? 1. We have the value of r as 1. So one thing is what we can do is we can just put the value of x by y. It is going to be, I'm not writing the whole equation as of now. We are going to get 1 plus 4 eta square because definitely r is going to be 1. And then in the denominator we'll have 1 minus r square. Now since r is 1, what are we going to get? We are going to get 4 eta square in the denominator. And we are going to have a square over here. So we can use this. We can find the value of eta. After finding the value of eta, we can get the value of C by using the relation of C and CC. That we have done already. But for now, we'll just see a different perspective for this question. If my question would have been to find out the damping ratio, I'll simply use this equation and it will give me an answer. Right? But then here I need to find out the damping constant. Now to find out the damping constant, first I'll evaluate the value of eta from this equation. Then I'll use the relation of Cc, which is twice of under root mk. I'll find out the value of Cc and then I'll multiply it. What if I want to use only one equation? Okay, so then there is the basic form of this equation, right? From which we derive this part. That basic form is nothing but x by y is equals to k square plus c square omega square divided by k minus m omega square plus c square omega square under root. This is the basic form of the equation, and this equation only is used in order to get the equation which is in the non-dimensionalized form, like in terms of eta and r. Okay. For this question, we already have the value of k omega, which is equals to omega n, and we need to just find out the value x and y we have, and we need to find out just the value of c. So if I put those values in this equation, what am I going to get? First, x is how much? X is 0.05. So 5 we are going to get over here. It is going to be equal to k square, which is 2500 square, plus c square, and then we need to find omega n, which is under root of k by m, and m is 25. So omega n is going to be 10 radians per second. So we'll have c square into 100, because we have omega square over here, divided by 2500 minus m omega square, which is 100, into 25. Anyways, this is going to be equal to 0, plus c square into 100. This will go to 0 definitely, because there is omega is obtained by using this equation, right? K minus m omega square is going to be 0 for omega is equals to omega n. So squaring on both sides, we have 25 is equals to 2500 square plus 100 c square divided by 100 c square. This will give us 2500 c square is equals to 2500 minus 100 c square, right? So this is going to give us 2400 c square is going to be equal to 625 into 10 to the power 4, or c square is going to be 2604.167667. Okay, and if I'll apply the under root, or if c is equals to this, the value of c will come out to be 51.0310 Newton second per meter. So this is going to be the value of what? The damping constant. Now the last question for the live session. So a spring mass system is subjected to coulomb damping. Coulomb damping means friction. When a harmonic force of amplitude 120 Newton and a frequency 2.517326 Hertz is applied, the system is found to oscillate with an amplitude of 75 mm. Determine the coefficient of dry friction if mass is 2 kg and K is 2100 Newton per meter. So this is a very simple like equation based question. So if you remember the equation, you can simply work on this. question. So for this question, we have a support, then we have a mass and a spring. There's no dashpot because we are talking about coulomb damping, right? Uh, the dashpot simply means viscous damping, but here we are talking about the coulomb damping. So there's going to be a friction, which is going to have a mu, which is the coefficient of friction, which we have to find out. Coefficient of friction. Mass is 2 kg, K is 2100 Newton per meter. Okay, and then there is a forcing. There is a harmonic forcing F of time, where F of t is of the form F naught sine of omega t, with F naught as 120 Newton, omega as 2.5173268 hertz. Okay. Then we have the system is found to oscillate with an amplitude of 75 mm. So for the system, if the response x of t is written something like x sine of omega t minus phi, capital X is given as 75 mm. Okay. Over here, what do we need to do is we need to find out the value of mu. Okay, which is the coefficient of friction. So for the Coulomb damping case, we have the relation of the form x is equals to 1 minus 4 mu n by pi f naught square divided by 1 minus r square whole square to the power 1 by 2 to the power 1 by 2. Now, for here, we need to find out the value of n, which is nothing but the normal force, n is equal to mg, and that is 2 into 9.81. Other than that, we need to find out the value of r, which is omega by omega n. Okay, this should be omega should be equal to 2 pi into this because it is given in hertz. The frequency is given in hertz. We need to change it into radians per second. Radians per second. So omega, we know we need to find out omega n, which we can simply do by using the equation omega n is equal to under root of k by m, which is 2100 divided by 2. This will turn out to be 32.403703 radians per second, right? So r, which is omega by omega n, will turn out to be 2 pi into 2.5173268. 2.5173268 divided by 32.403703. After doing all the calculation, this will come out as 0.488119. Okay. Now, if I put all these values, what am I going to get? See, we have 75 mm. Okay. So it will be 75 divided by 1000 is going to be F naught, which is 120 by K, which is 2100 into 1 minus 4 mu into 19.62 divided by pi into 120 square divided by 1 minus 0.488119 square. This whole to the power 1 by 2. So there is only one unknown variable over here, which is mu. Everything else is just numeric value. So after doing all the calculation, I'll write the final value. So it will turn out to be something of the form 1.3125 is equals to 1 minus 0.04334 mu divided by 0.5802 473 whole to the power 1 by 2, which may be further rewritten as 0.99566 is 1 minus 0.04334 mu square, and finally mu will turn out to be 0.1, which is the coefficient of friction. Okay, so I hope this question was clear. So this was it about all the questions for the week 5 live session. So we have gone through 10 questions which were mostly related to base excitation, and for the system when it is having some kind of excitation or basically harmonic excitation with coulomb damping. We did some questions related to unbalanced rotors and how are we going to deal with those kind of problems. So I hope this was clear and it will help you to solve the assignment problems. And so we'll meet next week. Meanwhile, if you have any query, you can ask in the next live session, or you can maybe mail to me at my email ID rashi_2121 me13 at the rate iitp.ac.in. Thank you so much, and we'll meet next week, Tuesday, 6 p.m.